Well, this little example problem is so interesting that we have to get right back to it. Okay, now, here comes the next step. Part C. Now, imagine that the compressed volume from part B is just large enough to offset the expansion in part A. Right? Remember in part A, the water expanded because of a temperature increase. And in part B, so the volume increased. In part B, the volume decreased, compressed, because of a pressure increase. Let's have these two volumes offset each other so that the volume of the water won't change when both of these things are happening. Okay? Both a temperature increase and a pressure increase. Right? You see how we're going to lead to getting the volume constant? That's how we're going to think about keeping the volume constant. All right. So using the fact that we're going to let those two volume changes equal each other in magnitude, then we're going to be able to get a ratio of dP to dt. Change in pressure to change in temperature. When we do get a ratio of those two infinitesimals, we're going to treat it as a partial derivative with the volume constant because we've expressly set up the volume changes to cancel each other. Okay? And they want me to find, in essence, the expression for that ratio, dP dt. Okay, so, part C. All we're saying to do is let the volume increase from the temperature increase in part A, dV1, be offset by the volume decrease from the pressure increase in part B. So I'm going to let dV1 equal the absolute value of dV2. And again, just thinking like physicists, just take these expressions for the dVs and set them equal, do an absolute value on this one, and you get thermal expansion coefficient times volume times temperature change, dt, equals isothermal compressibility times volume times pressure change, dP. Okay. Did I drop something? No? Okay. Notice that the volumes cancel, and I can form a ratio of pressure change to temperature change, dP over dt. That's just going to be the thermal expansion coefficient over the isothermal compressibility. Right? Now, I'll go from there to one slightly more fancy way to write this derivative. I'm going to write it as the partial derivative of the pressure with respect to the temperature at constant volume. That's the expression he wants. Okay? I'm going to actually number that equation, equation 1. We just got this relationship between pressure change and temperature change by offsetting those two volume changes. Now let me just do a little brief aside here. Something just happened in this step that I want to mention because it happens a lot, at least in that part of statistical physics that's traditionally called thermodynamics. Okay? So what I want to do is I want to plug in the definitions of beta and kappa T in equation 1. Right? What I'm going to get is something's going to look rather weird, but I'm telling you that it's useful in thermodynamics. So on one side of the relationship is going to be the partial of the pressure with respect to the temperature at constant volume. That's the left side of equation 1. Okay? On the right, I have the thermal expansion coefficient over the isothermal compressibility. For the thermal expansion coefficient, I'm going to plug in its definition right here. And for the isothermal compressibility, I'm going to plug in its definition right here. Okay? Notice there's one negative sign between this. I'll put that out front like that. So in the numerator, I'm going to have 1 over the volume, partial of the volume with respect to the temperature at constant pressure, in the numerator. And in the denominator, 1 over the volume the partial of the volume with respect to the pressure at constant temperature. Watch out with all these symbols. You've got to keep track of the symbols, including what's being kept constant. Well, obviously, the factors of 1 over v are common in the numerator and denominator, so I can reduce this to negative partial of volume with respect to temperature at constant pressure divided by partial of volume with respect to pressure at constant temperature. I'm going to number that equation 2. So what I'm claiming is that equation 2 is a valid relationship among partial derivatives of any triplet of quantities in this case, the triplet of quantities are pressure, volume, and temperature. Right? But in principle, this equation is valid among partial derivatives for any triplet of quantities that can be related to each other. You need something called an equation of state that relates P, V, and T in this case. Okay? Now notice what it says. If you look at it a little bit, you see a pattern in this relationship amongst the partial derivatives. And if you look at that pattern a little bit, you say, oh, I can kind of see why that pattern is correct. What I have on the left is the partial of P respect to P constant V. Okay? Now what do I have on the other side that I claim is equal to this? I've got two partial derivatives in a fraction. Again, if I treat these as ratios of infinitesimals, and then just use algebra of fractions, I could think of the two dv's as canceling each other. And then the dp, which is in the denominator of the denominator, actually goes all the way upstairs. And then I end up with a dp over a dt. The only thing you have to watch out for is the subscripts. All of these obviously are partials of one variable with respect to another, 2 out of the triplet, and then the remaining variable out of the triplet is always the one held constant. Now I'm contending that if you can come up with any three quantities that have some kind of equation of state relating them, think of an ideal gas, PV equals nRT. Okay. Then this pattern can be used to relate various derivatives of those three. Okay. No matter what the three variables are. Let's just show that it does work for the ideal gas, because we have a simple equation of state. Okay? So we're going to do a sanity check of equation 2 for the ideal gas. Okay? i.e., I'm going to compute explicitly that derivative, and that derivative, including the negative sign on the right-hand side, and show that the two sides are the same. Okay? All right. Now, when you do these derivatives, you must be careful, and you must be systematic and show all your work. So to do this derivative correctly, you have to express the pressure. You have to take the ideal gas law, right? That's our equation of state. So most people write that, let's say like that. PV equals capital N kBT. And now to use, first to this derivative, you must solve it for the thing you're differentiating. So solve for the pressure, N kBT over V. Then take the partial derivative of that expression with respect to temperature. And when you do that, treat the volume as constant. Which means the equation has to show clearly how it depends on both temperature and volume, so that you can show that you have differentiated with respect to temperature and that you have treated V as if it were constant. And of course, when you do this derivative with respect to temperature, treating V as if it's constant, you get N kB over V. So that's your derivative on the left side of this equation 2. Okay? Now let's check the right side. And now I've got two derivatives on the right side of equation 2. So let's do the numerator first. So what I have to do now is, since I'm differentiating the volume, I have to solve the equation of state for the volume, nkBT over the pressure. I've got to explicitly show that expression, so that I can then show you that I'm going to, in the numerator, take the partial derivative of this expression with respect to t, holding p as constant. So, partial derivative of v with respect to t holding p as constant is nkb over p. But I also need the partial derivative of the volume with respect to the pressure holding the temperature constant. That's the other derivative here in the denominator. Now again, this is the equation that I have to use because it's of the form v equals. So this is what I have to differentiate, but now I have to differentiate with respect to p, holding t as a constant, right? What do I get? Negative n kBT over p squared, right? It's just like y equals c over x squared, dy dx. Y equals c over x, dy dx. Okay? You see how I did this? You have to be very careful doing these partial derivatives and very explicit. It's not hard, but you can very easily make a mistake if you lose track of what's supposed to be held constant and what's supposed to be differentiated with respect to. Okay, now with these two derivatives, let's see what the right-hand side of equation 2 looks like. So I need negative. Okay, the derivative in the numerator, partial v respect to t constant p, is nkb over p, right? That's the numerator. And the denominator is negative nkbt over p squared. Right? Plugged in the two derivatives on the right-hand side of equation 2. Now I have two negative signs here multiplying, so that's going to make it positive. The nkb's are clearly going to cancel. This p squared can go all the way up to the top. This t goes here. I get one cancellation of a factor of p, so I believe I'm left with p over t. But the ideal gas law tells me that p over t is nkb over v. And that's what I had for the derivative on the left side of equation 2. So they are the same. So there's one where it's easy to show you that's true. I'm telling you that this combination, this pattern, I'm talking about the pattern you see up here, amongst three variables is generally true. For any triplet of variables, as long as you have some kind of equation that relates to three things. It's not very useful if you don't have that equation, but it's generally true, okay, for any three quantities. So now that's the end of that aside, okay? Because you will see, especially, we may very well a little bit later in the semester, but you will definitely, if you take a graduate level course in statistical mechanics that includes any thermodynamics, you will end up be doing lots of partial derivatives. You'll see. All right, now, with that in mind, I have done part C and more. So now let me get back to the example and finish it off with part D. Let's take water at 25 degrees Celsius. The thermal coefficient, the thermal expansion coefficient, is 2.57 times 10 to the minus 4 inverse Kelvin. And the isothermal compressibility is indeed a very small number, 4.52 times 10 to the negative 10, and apparently the units are that of inverse pressure. You see how that would come out in the definition? So inverse Pascal, notice how small that is, just as a number. Okay? Suppose you increase the temperature of the water from 20 degrees Celsius to 30 degrees Celsius. So these values they gave us here were right smack dab in the middle of the temperature range. How much pressure must you apply to keep the volume of the water constant? Because if you wanted to measure the heat capacity at constant volume over that temperature increase, you would have to keep the water from expanding. And you would have to do it by applying pressure. And we're now in a position to calculate this extra pressure that you would need to apply to the water. Because we're going to use equation 1 to show you how. Okay? Now all you have to do with equation 1 is write this fancy partial derivative as a ratio of two infinitesimals, dp over dt equals beta over kappa t, and solve for dp. Okay? So we'll rewrite equation 1 like this. dp over dt equals beta over kappa t. It's good to remind ourselves that this is at constant volume. And so we'll solve for dp. That's thermal expansion coefficient over the isothermal compressibility times the temperature change, dt. We can assume, since he just gives us constant values, numerical values of beta and kappa t, we'll assume that these quantities do not change over this temperature range for the water. Okay? So we treat beta and kappa t as constant. So you can write this expression in terms of finite changes in pressure and temperature. Delta P is beta over kappa t times delta t. You couldn't do that if these quantities weren't constant over the temperature range of this experiment. But we'll assume they are. It's not a huge temperature range, 10 Celsius degrees. So the thermal expansion coefficient is 2.57 times 10 to the negative 5 inverse Kelvin, which is also equivalent to inverse Celsius degree, 10 to the negative 4. And then the isothermal compressibility, 4.52 times 10 to the negative 10 inverse pascals. And the temperature change is 10 Celsius degrees. The units of Celsius degrees are going to cancel. The final result is going to have units of pascals, which it should because I'm solving for pressure. And what I get, the value I get for the pressure you need to supply to keep the water from expanding, I need to keep its volume constant, is 5.69 times 10 to the 6 pascals. So 5.69 megapascals. Right? Megapascals. If you want to think about it in terms of atmospheres, it's 56.3 atmospheres. So you've got to be pressing down on that water pretty hard. Okay? Now, using certain devices, such as what's called a diamond anvil, which uses diamonds to press something in on something, you can, or for very small areas, get pressures even 3 orders of magnitude more than this. Okay? So, gigapascal. So it can be done, but it can't be over a very big area, because these diamond anvils, well, first of all, they're expensive, right? And they don't tend to have a very large area over which they press. So, general point is, if you want to measure heat capacity at constant volume for the water, you're going to have to be able somehow to come up with some pretty high pressures. Just much easier to let the water sit there in the environment with the pressure all around it, just whatever it is, generally constant, and thereby measure the heat capacity at constant pressure. Okay. I I did this just to show you that most of the times in this book, well, a lot of the times, when you read the problems and it seems like it's really complicated, he's not being terribly complicated. But it seems like it at first. Okay? Just FYI. Okay, now, just a little bit more about chapter 1. There's a little bit more reading. The section towards the end. This is not on Thursday's quiz. Some of which I'm leaving for you, and some of which I'm going to talk about briefly. I'm going to leave for you to read pages 32 and 33, which talk about what's called the latent heat of a phase transformation. I'll remind you that, let's say you have a sample of ice at 0 degrees Celsius, so right at its phase change point, and you add energy as heat, Q. Right? You know that what happens when you have a material at its phase change point and you add energy as heat is it starts to undergo the phase change. Okay? And remember that while a material is undergoing a phase change and you're adding energy, its temperature stays constant until every part of it has changed phase. So you can ask yourself, how much energy as heat Q must you add to your sample in order to get it to entirely phase change? Answer, the mass of the sample times the quantity that's called the latent heat. And that depends on what the material is and what kind of phase transformation is it. Right? Obviously there's the solid-liquid phase transformation. Anybody know what that's called in physics? Remember? Solid-liquid phase transformation. I mean, there's the everyday word like melting and freezing, which you can use. But physicists use the word, you just said it, fusion. Now that has nothing to do with the nuclear process known as fusion. Absolutely nothing. But that phase transformation is sometimes called fusion. So if somebody talks about the latent heat of fusion of water, they're talking about the latent heat for the phase transformation between solid and liquid. Now there's a transformation between liquid and gas. That's called the latent heat of vaporization. There is, as you may know, a transformation from gas to solid. And all of these go both ways, right? You could go solid to liquid, liquid to solid, liquid to gas, gas to liquid, and solid to gas, gas to solid. That has a latent heat too. Anybody have to know what that one's called? The latent heat of? That one's not so very well known.
From gas to solid.
It's a gas solid. It's called sublimation. Okay? The common example of gas, of solid to gas directly, is solid CO2. It goes directly to a gas. You know what that's called, right? Solid CO2. Dry ice. Goes directly from a solid to a gas. So you get the vapor coming off of it, right? People use it for effects. Spookies. Okay? But things can go from gas directly to solid. Technically it's called deposition. The most common example of that in nature is frost. When frost forms, you go from water vapor to ice crystals directly. Okay? So that does happen. So you can read about the latent heat for its material dependent and phase change type dependent. But we talk about that in Physics 111 for a while. Okay? So I'm going to leave that to you. But I'm going to introduce to you, mainly just so you'll start to get used to it, a new quantity that chemists love. Physicists don't use it quite so much, but I want to talk to you a little bit about why it can be helpful. So we're starting a new section now. I think I'm up to 8. And this new quantity we're going to define has a rather interesting name. It's called enthalpy. And it is useful for constant pressure processes. If you think about it, most chemical reactions occur in a constant pressure environment, so this is why chemists are interested in this quantity. So the motivation is the fact that I just said. Many experiments occur at constant pressure. Whenever your sample is just immersed in something like air, that's assumed to be constant pressure. Okay? An example is measuring, obviously, the heat capacity at constant pressure. That's very neat. Let me remind you, by the way, when we talked about measuring heat capacity at constant pressure, remember that is the heat energy that must be added to make the temperature go up by 1 temperature unit, with the pressure being held constant. We found that when you added that heat energy in this situation to your sample, with the pressure held constant, 2 things happened. Okay? You made the temperature go up, and work was done to expand against the pressure. Okay? All right. That's just an example. Now, let's suppose you want to create an object with some amount of, basically, total energy. We'll just limit that to internal energy, U. You want to create something that has some amount of energy, internal energy U, and volume V, while it's placed in a, what we'll call, pressure bath with pressure P. Okay? How much energy must you provide to do this? What is the total required energy to do this? This thought experiment. Okay? You have some object. Okay? Maybe it's a chunk of aluminum, and you want to create it. Don't worry about how you would do it, but you want to create it. It's going to have some volume, it's going to have some energy, total internal energy U, and it's immersed in a pressure bath where the pressure is P. How much energy will you have to provide? I'm just asking how much energy you'll have to provide. Okay? All right. Well, you have to provide the amount of energy equal to the internal energy, however much that is. That's how much you got to provide. But that's not all. Because you don't get to put it, it's like rent. You don't get to put it in the pressure bath for free. It's got to pay rent. And by paying rent, I mean you've got to do work to displace the volume V, to put the thing in. Okay? So you're going to have to do work against this pressure bath to insert the thing in there. You're going to end up pushing stuff aside. Okay? And so, how much work are you going to do? Well, if the pressure is constant, it's just going to be the pressure times the volume change. Well, the volume change is the volume of the thing. So, P times V. So remember that this product of P times V is the work needed to push aside the environment to make room for the object. Okay? Now, there's a converse to this too. If you already had, say, a chunk of aluminum in a pressure bath with some internal energy U and some volume V in a pressure bath P, and you destroyed it, again, don't ask how you would do it, you just destroyed it, how much energy would you get? Well, it would be devastating, but because it'd be a lot. but it would be that same amount. The total internal energy of the thing thing that would make it so big, by the way, would be the mc squared part. But you get a little more than that. You would also get energy when the pressure, when the environment rushed in and filled that volume V. Collapsed, if you like, to fill the volume V that the sample had taken up. And if you had a way to harness that, rushing inward, that's work, you could use it. So it's energy. Okay? Okay, so what we're talking about is that if you've got objects immersed in a pressure bath, then it might be at least beneficial to consider, in terms when you talk about its energy, not just its internal energy, but this product of P times V. So what people have done is they have defined a quantity. They've just defined a quantity that has dimensions of energy. So you can call it a form of energy. All forms of energy are just convenient definitions. Right? So we're going to define another form of energy. So we're going to define a new quantity with dimensions of energy. And this quantity is called, say, enthalpy. I don't know where the name came from. I have to look that one up. It's historical. And what's the symbol for enthalpy? Capital H. Now watch out for physics people, that does not mean Hamiltonian. Okay? You'll see in a minute where the symbol H comes from. But it is defined to be, for any system, if you define it this way, the internal energy of the system plus the pressure bath it's in times its volume. Okay? Now, again, in that part of statistical mechanics known as thermodynamics, you do this a lot. You start with the internal energy, and if the material is immersed in a bath, where something in that bath is constant, you find it convenient to add, or sometimes subtract, the constant times some other property of that material, so that that combination has dimensions of energy. And thereby define a new form of energy. And it turns out to be convenient to do that whenever the system is immersed in some kind of a bath. Pressure bath. Later on we're going to have immerse things in a temperature bath. Okay? Yes?
I guess what I'm just confused is you're saying like energy PV, is that a new form of energy? Because when I think
It's energy, it's energy that you get because the environment basically does work when you take the thing away because it had a volume V. So the environment does work because it collapses in to fill the vacuum that you just made. Okay? And you could, if you had some kind of a mechanism sitting there, you could use the work from that collapsing environment to do something, like turn little gears and wheels on a mechanism. Okay? So I'm just saying that it's ultimately energy that can be then show up in other places, like kinetic energy of things moving. Okay? So somehow, if you contrived your apparatus carefully, you could measure that effect. Because it would show up in some other form of energy that you could detect. Okay? Okay. Now let me take this definition of enthalpy. That's the definition, 3 lines. It's defined to be that. Right? We could define things all day long if we wanted to. It's not always very useful just to do that. Right? But you're going to see a pattern later on this semester where we do this quite a bit, this kind of definition. Let me take this in a differential form. We do that a lot too in statistical physics. We imagine infinitesimal energy transfers and changes. So if I write this definition of enthalpy in terms of differentials, a differential change in enthalpy of a system can come from a differential change in internal energy, plus, remember this is a pressure bath, so the pressure isn't going to change, plus P times an infinitesimal change in volume. Okay? Constant pressure. I'm going to number that equation 1. If you like, that's the infinitesimal version of enthalpy change. Okay? Let me combine that, 3. Let me combine that expression with the first law. So equation 1 with the first law of thermodynamics. Let's write the first law also in differential form. Okay? So an infinitesimal change in internal energy, du, according to the first law, can have 2 contributions. There can be an infinitesimal energy transfer as heat. Note, by the way, I'm writing it. dq bar. Watch out, warning, your book would just put the symbol Q here. But this means it's an infinitesimal transfer of energy as heat. Plus an infinitesimal energy transferred as work being done on the system. Okay? So that's the first law of thermodynamics written in infinitesimals. Yes?
Can you tell me why is it again that you put the bar over the
Okay, so remember, the bar versus no bar is an important distinction about the physical nature of these 3 differentials. This one is what's called an exact differential. This really means a change in internal energy. Meaning that the system had some initial internal energy, U1, and some final internal energy, U2, and this is the difference between U2 and U1. These 2 are called inexact differentials. They do not represent infinitesimal changes. This does not mean infinitesimal change in heat. Because to say those words is to imply that the thing had an initial amount of heat, Q1, and a final amount of heat, Q2, and that this is just the difference between them. But that's not right, remember? Because systems don't have an amount of heat. This just represents an infinitesimal amount of energy that went in or out because of a temperature difference. This means an infinitesimal amount of work, or energy, that went in or out by work, i.e. by means of a force. Okay? Okay. Now, let me also just make a comment about this infinitesimal work done on the system. This is a total amount of work done on the system that can, in principle, come from many contributions. And things can get really interesting if you really start to look at this. But I'm going to break it down into 2 parts. dW on is, all the work's going to be classified into 1 or 2 groups. It's either expansion compression work from a volume change of the system. We know how to write that in infinitesimal form. It'd be negative P dV. That's how you represent expansion compression work from a volume change. But then there could be other forms of work. There could be electrical work. If there's a battery connected to wires that's pushing charges around, and that's part of your system. Okay? Or if the battery pushing charges in a wire, i.e. making current, is causing a magnetizable object to develop magnetization, that's work, but it's not P dV work. Okay? There are a lot of things that can be over here, in general. But we are mostly going to focus on that. Okay? Expansion and compression work. So now what I'm going to do is combine equations 1 and 2. Okay? Let's combine equations 1 and 2. So, an infinitesimal change in enthalpy of the system is an infinitesimal change in internal energy, du, plus pressure times volume change, pdv. Now I substitute in, for the du, the first law of thermodynamics, equation 2. du is a tiny heat transfer, dq bar, plus a tiny amount of work done, d bar W on, which is negative P dV plus d bar work other. So that's, in parentheses, equation 2. And then from the definition of enthalpy, I add to that plus P dV. And then I see that there's a negative P dV and a positive P dV. And I discover that there are really only two things that can cause a change in enthalpy. A tiny heat transfer, dQ, and then any amount of work that's done that isn't expansion compression work. Okay? This is non-expansion compression work. Now a lot of times, so if this other amount of work happens to be 0, which will be very common for us, if this other amount of work is 0, then there's only one way for the enthalpy of a system to change. Heat must go in or out. Okay? And that's why the symbol for enthalpy is H. H for heat. Okay? All you have to do, all you have to know, if you want to know how much the enthalpy has changed, is how much energy went in or out as heat. You don't have to worry about, did it expand or compress, PdV stuff. Don't have to worry about it if you're keeping track of enthalpies. And that's what chemists like to do. Okay? So I just want you to get used to this. We're not going to use it for a while. Okay? But I want you to get used to the idea of defining a new form of energy. That's just a definition. By starting with the internal energy, and then adding, or sometimes we'll subtract, a product of two quantities that has dimensions of energy. Okay? I'll close with one other note. 4. Let me remind you that we've already seen, let me go back to something, the heat capacity at constant pressure, right? This whole section with enthalpy is about constant pressure. Okay? The heat capacity at constant pressure had two terms before. The rate of change of the internal energy with respect to temperature at constant pressure, plus the pressure times the rate of change of volume with respect to temperature at constant pressure. Remember it had the two parts? C sub P? And then it's a little bit of a pain to keep track of this one over here. Now just use equation 1. Look carefully at equation 1. Now again, think like a physicist. Equation 1 is the infinitesimal version of enthalpy change. Divide through by an infinitesimal temperature change dt. Divide by dt, divide by dt, put the dt under the dv. Think of those then as derivatives. Okay? All those derivatives will be at constant pressure. And you will see that you have another way to write heat capacity at constant pressure. It's the partial derivative of the enthalpy with respect to temperature at constant pressure. One term only. The rate of change of enthalpy with temperature at constant pressure. Will we use that a lot? Probably not, but I bet chemists do. Okay? Chemists have tables where they look up something called the enthalpy of formation of things. You'll even find them in your book, this book, in a table at the back. Okay? These are things that have been measured, and they go right to these tables, so they know how much enthalpy gets formed, liberated, or is required, must go in for a chemical reaction to occur. So chemists worry about this a lot. I'm introducing it more mainly to get you used to the idea of what I've just said up here. Starting with internal energy, adding or subtracting a product of two things that has dimensions of energy to get a new form of energy by definition. And then, like I said, this is most convenient when the system is immersed in a bath where something is held constant. In this case, it's the pressure. But we'll do other things later, like different baths, like I said, like a temperature bath, where the temperature is constant. Okay? Okay, so that is all I'm going to say about chapter 1. That's all you're responsible for, chapter 1. Okay? So on Thursday, well, we're going to start chapter 2. Okay.
Just see.